Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to be going over how to use molarity as a conversion factor in equation stoichiometry. So let's get into this. So in previous videos where I've done stoichiometry, I've used a roadmap, and so what you see here is the roadmap, but it's been built onto, right? So when we've done mass to mass conversions, mass of one substance to mass of a different substance, we would start with the mass of substance one at some unit, right? We would need to convert that to grams in order to use molar mass to convert grams to moles. So we would have to use some conversion to convert 2 grams and then use the molar mass of substance one to convert to moles of that substance. And then once we got to moles, we can now use the mole ratio from the balanced equation to convert from moles of one substance to moles of the other substance. So what I've always said in stoichiometry problems is that the goal is to get to moles. So whatever unit you're given, get to moles. So now we're introducing molarity. So molarity is a conversion factor, or it's a measurement that you can use as a conversion factor to convert between volumes and moles. So in this case, if you're given the molarity and the volume of a substance and you want to get to a different substance, you can use molarity as a conversion factor to do that. So here we got an offshoot, like maybe this is your main highway as I call it, and then this is your off road, right? Maybe it's a local highway, and then you're gonna get in onto the main highway. So local roads lead to the highway. So here you're gonna start with some volume, unit of volume. If it's not already liters, then you're gonna have to convert that to liters. Once you've got liters, you can use molarity to convert liters to moles. And once you're there, you can go anywhere on the main highway. Okay, you can even go off the main highway off of another side road to get to your destination. So let's go ahead and apply this to our problem. So the way that I do this is I use molarity as a conversion factor, and I just convert all the way through like I normally do. So they're asking what volume of a 6.00 molar hydrochloric acid solution is necessary to neutralize and dissolve 31.564 grams of solid aluminum hydroxide. So here we have a base, here we have an acid. It's an acid-base neutralization reaction. And in this case, we're given the grams, the mass of a solid, and we want to know what volume of this molar HCl is needed to dissolve completely that mass of our aluminum hydroxide. So here, they're giving us molarity. Whenever you see molarity, you should be thinking conversion factor. We're not going to start with molarity in our problem. You never start with a conversion factor. So we're not going to start with 6.00 molar. The only other information we're given is that we have 31.564 grams of the aluminum hydroxide. So we're going to start there. So we're going to take 31.564 grams. And again, this is the aluminum hydroxide. That's the formula for aluminum hydroxide over 1. And so where are we starting on our roadmap? We're starting with grams. So we're starting with grams of substance 1. So we're going to convert that to moles right away using molar mass. So I need the molar mass. So you have to calculate the molar mass using your periodic table. So here I calculated as 78.0036. So I put 78.0036 grams of the aluminum hydroxide. And then on top is going to be 1 mole of the aluminum hydroxide. And that should be a 3. Let me make that better. There we go. So grams cancels out, and now I have moles of the aluminum hydroxide. Now I can use the mole ratio in my balanced equation. But we need a balanced equation. I totally forgot. So we're going to need a balanced equation. So balanced equation, we're going to start with the reactants. So we have HCl as one reactant. So we have, I'll write it down here. So HCl, that's going to be aqueous plus, and then we have aluminum hydroxide. That's going to be a solid. So AlOH3, that's a solid. And that's going to form a couple of products. Now, to form the products, again, to do a neutralization reaction to predict what your products are going to be, you're going to treat this like a double displacement reaction with two ionic substances. Even though your HCl is not an ionic substance, it will ionize. So you can put the outside ions together. So hydroxide and hydrogen is going to form water. So that's going to be one product. That's going to be liquid water. And then the inside ions go together. So aluminum has a 3+ charge. How do I know it has a 3+ charge? Well, because it's in group 3A of the periodic table. Plus, I know that hydroxide has a -1 charge, and I have 3 negative hydroxides balancing the charge on aluminum. So aluminum has to be a +3. So this is a +3. Chloride ion is a -1 because it's in group 7. So I'm going to need 3 chloride ions to balance the charge on the aluminum. So let's go ahead and do that. So that's going to be, where's my alumina? Yeah, so there it is. So Al and then Cl3 is going to be the other possible product. And again, given the fact that this is a chloride and we have aluminum, it's going to be insoluble. So it's going to be aqueous according to the solubility rules. And so now that I have my equation here, this is the neutralization equation for these two substances. And so now I need to balance it. So here, I'm going to balance the metals first and then the nonmetals and go from there. So aluminum, I have one aluminum here. I have one aluminum there. That's balanced. Next, I'm going to do the nonmetals. I'm going to do chlorine first. So chlorine, I have one chlorine here. I have 3 here, so I'm going to have to put a 3 here. So that's balanced now. Now I'm going to do the hydrogens. So hydrogen here actually comes together with hydroxide. I have 3 hydrogens and I have 3 hydroxides. Those are going to come together to form water. I should have 3 waters here, right? Because each one together forms one water molecule, and I have 3 each, so that's going to form 3 waters. So now I have a balanced equation. So now I can use the mole ratio in my balanced equation. So I need the mole ratio between these two. So it's 3 moles of HCl to 1 mole of the aluminum hydroxide. So I'm going to put moles of aluminum hydroxide on the bottom. Right, since I have moles of aluminum hydroxide on top, I'm going to put 1 mole right there on the bottom. So 1 mole of the aluminum hydroxide on the bottom, and I have 3 moles of the HCl. That's going to go on top. So 3 moles of HCl. So here, moles cancel out. Now I have moles of the HCl. So I have 3 moles of HCl. Now I can continue on. What do they want me to find? They want the volume of HCl. Well, in here, they don't tell me the unit, but let's go ahead and convert to milliliters. Usually we're measuring this stuff in milliliters anyway. So we're going to have to use the molarity to convert moles to liters. So let's go ahead and do that. I'm going to bring it down here for fear of lack of space. So I'm going to use the molarity. This tells me 6.00 molar is 6.00 moles of HCl per liter of HCl solution. So I'm going to continue here. Since I have moles on the top, I want moles of HCl. So 6.00 moles goes on the bottom. So moles of HCl on the bottom, and 1 liter of HCl solution. I could put solution in here to distinguish from moles of HCl. So here now, moles of HCl are going to cancel out. Now I have liters. Now I can convert that to milliliters using the conversion factor between liters and milliliters. So I have liters on the top. So I'm going to put 1 liter on the bottom. 1 liter of whoops. Sorry about that. So I have 1 liter of HCl solution goes on the bottom, and then that means that 1,000 milliliters or 10 to the third milliliters of HCl solution goes on top. So the liters of HCl solution cancel out. Now I have milliliters, so now I can go ahead and calculate this out. And when I calculate it out, I get 202 milliliters of HCl solution. And that, ladies and gentlemen, is how you get it. So now, for this, for those of you who are interested in the sig figs, how do you figure out the sig figs? Again, the answer, whenever you multiply and divide, as we are here doing the conversion factor method, your answer should have the same number of sig figs as the measurement with the least number. We're going to ignore anything that's exact. So any metric volume to metric volume, that's going to be exact because we have metric units related to each other. Again, here, that is a mole ratio. Mole ratios are exact. And so what we're going to do, focus on, is the molar mass here. So the molar mass here, this has 6 sig figs there. The molarity that they gave us has 3 sig figs, and then the mass they gave us has 5. So the least number of sig figs is 3, so therefore our answer is limited to 3 sig figs. And that, ladies and gentlemen, is how you apply molarity in the pursuit of solving an equation stoichiometry problem. So I hope this was helpful. If you enjoyed this video, then please, by all means, like the video, share the video with your friends, hit that like button. Also, make sure that you subscribe to my channel. When you do, make sure you click that notification bell and click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem you want me to go over for you, or if you have a question you want help on answering, or if you have a topic you want me to cover, I would love to do that for you. Thank you for joining me. Have a great day.